Yesterday we talked about how to evaluate limits using a table, which was the numeric method, and looking at a graph, which is graphically. Today we're going to talk about how to evaluate limits analytically. The methods that we use for analytical evaluation of a limit is, first of all, direct substitution. You should always use direct substitution first, no matter what other way you're going to try to possibly solve a limit analytically. Always try direct substitution first. If that doesn't work, then you can choose the other methods, but you must always try direct substitution first. And it is as you would expect. It means you take the x value that you're trying to approach, as x approaches 2, and you directly substitute it into the function to see if you can actually calculate the y value. So in this case, don't use an equal sign because I'm not writing the word limit over and over again, and so I don't want to have to show two, what I'm going to write is not really equal to what I have on the left side, because the limit as x approaches 2 is not always necessarily equal to what I'm trying to do. Sorry about that interruption. So do not use equal signs if you don't want to rewrite the whole thing over again. And since I don't want to rewrite limit, I'm just going to write this. I can use an arrow to show that my thinking proceeds this way, but I know it's not actually equal, or it may not actually be equal. And so 2 squared is 4, 4 times 4 is 16, 16 plus 3 is 19. If you actually get a number, that's the limit. So this limit does equal 19. Here, if I put a 3 in, that simplifies to secant of pi over 6 times 3, which will be secant of pi over 2. Looking at my unit circle, pi over 2 is here. Secant is 1 over cosine of pi over 2. Cosine of pi over 2 of that value there, of that point there, is the x value, so that's 0. So I have 1 over 0, which is undefined. So that would be an example of the whole, or one of the other ways that a limit fails to exist. And we'll have to do more work to figure out exactly what that is, but right now we're just going to say limit does not, you didn't even have to say the L there. The limit does not exist. Simplification is the second option that you use if you can't just use direct substitution. You factor and cancel, and then you use direct substitution. On your homework, it's going to ask you to find a function that agrees with the original function at all but one point. It'll also say that on tests. So what that means is just you're going to simplify the function, cancel out something, so your new function is actually not completely equal to the original function. It agrees with the original function, which means it looks like the original function on a graph everywhere but one certain point. So I'll show you an example of that. This computer's being very slow. Oh. Okay, if we graph this, we're going to have a hole at -3. A hole at -3. Let's try direct substitution, which is always our first option. So we're going to plug -3 in for x. -3 squared is 9, minus 3 minus 6. So we get -9 on the top. I'm sorry, -0 on the top. 9 minus 9 is 0. And 0 on the bottom. So this limit appears to look like it goes to 0 over 0, which is what we call an indeterminate form. There are lots of things we need to do with indeterminate forms in the future, but at this point what you need to know is it is something we cannot determine. We cannot determine the limit. So we have to change this function so that we can find the limit. So what we're going to do is factor the numerator. X times x is x squared. 3 times 2 gives us 6, and if we do a positive 3 and a negative 2, that'll give us the middle term of x. So now this function is still exactly the same as the original, but we can cancel this. So now we have a new function. This function agrees with the original function at all but one point. If you graph the function f of x equals x minus 2, oops, missed that. It's going to go about like that. If you graph this function, the original function that we had, it's going to go right on top of it. It's going to agree at every point except there. It's going to have a hole there. So the green function is the original, and the purple function is the new function, this new function that we found that agrees with the original function at all but one point. And that specific point right there is where they disagree. The green function does not have a point there, it has a hole, but the original function does have, the x minus 2, the new function, does have a point there. So what we're going to do is use this new function to find the limit analytically. So now let's try direct substitution. Plug negative 3 into that function and you get negative 5, which in fact is the y value of that hole. There is a hole on the purple function at negative 3, negative 5. There is a hole on the green function at negative 3, negative 5. The purple function actually has that point. So we can say that the limit of this original green function is negative 5. Because remember, a limit exists as long as the two sides of that graph are approaching the same number, the same y value, as x approaches that y value, which would be negative 3, which I didn't draw it in a very good place. Graph paper would have been more helpful. So the limit of this equals negative 5, and if we did not have the graph, so if you didn't have a graph to look at, analytically you factor, cancel, and then evaluate using direct substitution the new function that you found. That will give you the actual limit of the original function. And thirdly, rationalizing. If direct substitution doesn't work, you rationalize, which is multiplying by the conjugate. Let's try this function. The limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. If we try direct substitution, which is what we're always supposed to try first, we get 0 plus 1 in the square root over minus 1 over 0, which is 0 over 0. Again, indeterminate form, which means you don't know the answer. It can't be 0. It might be 0, might not be 0. We can't tell exactly what it is until we do something more with this problem. So we're going to take this and think about factoring. Oh, can't factor that. So our other option is multiplying by the conjugate. The top has a conjugate of the square root of x plus 1 plus 1. You just change that symbol, not the one inside of the square root. And then do FOIL. First times first, the square roots go away. Outside times outside is the square root of x plus 1. Inside times inside is the negative square root of x plus 1. And last times last is minus 1. The denominator, we do not want to multiply it together. You hardly ever want to multiply denominators together because you will usually end up with something canceling. You always want to multiply out the numerator so that you can simplify and refactor if necessary. Now we can cancel these two. They add up to 0, which is the great thing about rationalizing. So you end up with x plus 1 minus 1 over the quantity x over the square root of x plus 1. plus 1, which continues to simplify to x over x times the quantity of the square root of x plus 1 plus 1. Those x's cancel. Remember, you're left with a 1 on the top. I can't tell you how many brilliant students I know continue to cancel and forget that there's a number on the top, and they just say that this is the answer without a number on the top, so it's just incorrect. That's still in the denominator. Now let's take the limit of this new function as x approaches 0. Direct substitution gives us the square root of, gives us 1 over the square root of 0 plus 1, which is 1 over 1 plus 1, which is 1/2. So this indeterminate form turned into 1/2. The previous one, 0 over 0, ended up at -5. So 0 over 0 is not an indicator at all about what the answer will be. But if we graph this and we look at values as x gets closer and closer to 0, or make a table of this as x gets closer and closer to 0, we will see that the y values approach 1/2. So the limit is 1/2. And we found that without a table or graphing. This is called analytically. Remember, always try direct substitution first, then try factoring and canceling. If that doesn't work, then you can multiply by the conjugate if possible. Theorem 1.5, limits of composite functions. If f and g are functions, such that if we're trying to find the limit as x approaches c of some function g, that answer is L. And then we want to find the limit as x approaches that L, so whatever number that was, that's what x is approaching for this function of f of x. And that equals f of L, which meant direct substitution. You just took that L, that answer you got from g, and plugged it into f. If that's true, then we can say that the limit of f of g of x as x approaches c is just f of L. So g was the function we plugged c into, and the answer we got that came out of that was L, and then plug L into the f function. So it's just saying that if you have a composite function and you know the limit of the inner one, you can take that limit and plug it into the outer one to get the answer and not have to do all the calculating with the composite function. Let me give you an example. So if you have f of x equals the square root of x, and you have g of x equals x squared plus 4, and you're supposed to find the limit as x approaches 0 of f of g of x using that theorem 1.5. Without using the theorem, we could take g of x and plug it into f and then plug 0 into that. But using the theorem, we first find the limit of the inside function as x approaches that number. So direct substitution will give us 0 plus 4, which is 4. So that's the L in the theorem. Then what we're going to do is take the limit as x approaches that 4, that answer we got here, and put it into the f function. Direct substitution gives us the square root of 4, which is 2. So let's just check it using composite functions just to show you that it does work. If we did f of g of x, we would have the square root of, and then take that x squared plus 4 and plug it in. So if we're trying to find the limit of that as x approaches 0, direct substitution gives us 0 squared plus 4 and a square root, which is the square root of 4, which is 2. So you see you get the same answer. Well, then why do you need that? Well, on the AP exam, they don't always give you all the information. They might say f of x is 4x, and they might tell you what the limit of g of x is, but not actually tell you what g of x is. And they'll say, find the limit as x approaches 2 of f of g of x. They are notorious for asking questions like this. They only give you part of the information, so the only way to go about it is using the theorem that you should know. So remember what the theorem says. It says that if you plug 2 into g and get that limit, then that limit can get plugged into f, and that'll give you the limit of the composite function. So what we're going to do is plug this, because that part is plugging 2 into g of x. Take that 4 and plug it into f. That's according to theorem 1.5. We can do that. So f of 4, take the function 4 times x, and in this case our x is 4. We're plugging 4 in place of x. So that limit is 16. There are some properties of limits we need to know. If you're trying to find the limit as x approaches some number of a constant, that will just equal the constant. For example, the limit as x approaches -1 of the horizontal line 12 will always just be 12. If you want to find the limit as x approaches c of the function f, either added or subtracted to g, so this is two properties merged together, limit of f of x plus g of x and limit of f of x minus g of x. Either one of those will equal the limit as x approaches c of f of x plus or minus the limit of g of x as x approaches c. So what that means is if I wanted the limit of the sum of the two functions, I don't have to add them together first and then plug c in. I could find the limit of each one and then add or subtract the answers depending on what this was. And that works with multiplying also and dividing. You can multiply them or divide them in any order. So it's almost like limit is distributive. You can add or subtract or multiply or divide the functions together first and then take the limit, or you can do the limit of each piece and then use the operation inside there. And that works with powers too. For example, let's say we're given that the limit as x approaches c of some function, so we don't know barely anything about this, but we know it equals 5. And we also know that the limit as x approaches that same c, the c has to be the same, just so you know, of a different function equals 10. So we've got two different functions, but as x approaches the same x value, they have two different y values. Then let's say we're supposed to find the following. Let's find the limit as x approaches c of the function f of x squared. So instead of squaring the function first, because we don't even know what the function is, we can just square the answer of the limit. So that would equal 25. And another example, if we're supposed to find the limit as x approaches c of g of x plus itself, we don't know what g of x is, so we can't add it to itself and simplify it and plug c into that. But we can say we know the limit of g of x is 10, and we know the limit of this g of x is 10. So we can just add them together and get an answer of 20. And I just have one more example for you. The limit as x approaches 0. And the way your book writes it is like this. I don't want you to be confused by this type of problem when you come across it on your homework, so I want to work through it. This is really this fraction, and that is that fraction. So we've got a fraction minus a fraction all in a big fraction. And what we want is the limit of that. If you try direct substitution, you get 1/4 minus 1/4, which is 0 over 0. So direct substitution gives you 0 over 0. Indeterminate form, which means we need to do something. So we can't factor it, we can't really multiply by the conjugate. The thing we're going to do is simplify it in a different way. We're going to get a common denominator. So our common denominator would be 4 times x plus 4. So we're multiplying this by 4 over 4, and we're multiplying this one by x plus 4 over x plus 4. That way, our new fraction is 4 over 4 times x plus 4, and this fraction is x plus 4 over 4 times x plus 4. All that is still over x. I'm not writing an equal sign because I'm not going to keep writing the word limit. I'll just use arrows. So now I can combine those into one fraction with the common denominator of 4 times x plus 4. So I have 4 minus. Now I'm subtracting this whole fraction, so make sure that you distribute the negative sign to both the x and the 4. And that's all over x. Continuing to simplify, on the top I have negative x, and then I have 4 times the quantity x plus 4 over x. So now I have a fraction divided by x. To simplify that, I want to multiply by the conjugate of the denominator. What's the conjugate of x? It's 1 over x. So multiply those. I want to cancel the x and the x. So I still have a negative 1 on the top, and I have 4 over x plus 4. 4 times the quantity x plus 4. Now that I've simplified this, I want to take the limit of it. So I've got a new function that's similar to the first one. It's equivalent, but I'm going to try direct substitution in this one. It's just a different form, and maybe I'll get an answer that is not indeterminate. And I do. So now I have the limit of this function, which is negative 1 over 16. So that type of problem will be on your homework. Make sure you know how to do that. And ask me questions if you have any. Your homework for today, well, that we'll work on in class, is going to be page 67, 1 through 59 odd. And you're welcome to get started on that if you'd like to.